Which chi-squared test do we use in different situations? So I want to break down the goodness of fit test, the test of homogeneity, the test of independence, and see how they're different from one another. The goodness of fit test, we have a single sample and we're measuring one variable. Now that variable has more than two values, okay? So for example, in our regular M&Ms example, we had one sample of regular M&Ms and we had one variable, M&M color, but it could take on 6 different values, brown, blue, orange, red, etc. The question we want to answer is the distribution of the variable. Does the data show convincing evidence that the distribution of the variable is different than the claimed population distribution? In other words, does our data show evidence that the claimed distribution of colors in M&Ms is correct, or is it not correct? Okay, so that's what we're looking at. So we just have a single sample, a single variable compared against a claimed population distribution. In a chi-square test of homogeneity, we're looking at 2 independent groups. So this is where we looked at the dark and the milk chocolate M&Ms, and we're comparing them to each other. So we're looking at one variable, still, the M&M color, with more than 2 values. It has 6 different colors that we're looking at, and we want to know if the distribution of the variable is different for the 2 groups, specifically for the 2 populations, I should say, for the 2 populations, not just the 2 samples. Okay, then the next one, we have a chi-squared goodness of fit test. I'm sorry, I don't know why I wrote that down. This is a chi-squared test of independence. Wow, 2 mistakes here. Chi-squared test of independence. Both of these are displayed on a two-way table. This has 2 different groups and 6 different M&M colors. You know, one variable of colors, but 6 different colors. So this would be like a 2. This was a 2 by 6 here. Here we had one sample of pregnancies. When the test of independence, the difference between that and homogeneity is we're only doing one sample, not 2 independent samples. So we only have, and actually with a homogeneity, you could have 2 or more independent groups. We could have compared milk chocolate, dark chocolate, and peanut M&Ms and looked at their colors and said, are they all the same? So here we have one sample of pregnancies, but we asked 2 things, the age and the result of the pregnancy. So we have one sample but 2 categorical variables, and what we want to know is there an association between those 2 variables in the population. Now we have one other situation where we have a two-way table where we don't actually have to do a chi-squared test. We could, but we don't have to. If we have a two-way table with 2 independent groups and one variable, but that variable only has 2 possible values, then we can compare proportions using a 2 proportion z-test. So basically our question is, are the 2 proportions not equal to each other? Is one greater than the other, or is one less than the other? So if we had only 2 M&M colors, say blue and orange, we could say, is the proportion, we could pick either of the colors and say, is the proportion of blue M&Ms the same for both groups? If that's all we cared about. If we were just caring about that one color versus the other color, or that one color versus the rest of the colors, we could do a 2 proportion z-test. So let's take a look at an example here that might help, or a couple of examples that might help with this. It says an article in the Arizona Daily Star included the following table. Suppose that you decide to analyze these data using a chi-squared test. However, without any additional information about how the data were collected, it isn't possible to know which chi-squared test is appropriate, although we can make some educated guesses about that. The first question I want to clear up is about the whole idea about age being a quantitative variable. Age is a quantitative variable if you can take in, if age can be any number between any number between this and this, and it includes all numbers. But when you break age into groups like this, it becomes a categorical variable, because then we can count how many are in each age range. Okay, so that is if you had a question about that, I wanted to clear that up. Second question, how do you know that a goodness of fit test is not appropriate for analyzing these data? Well, there isn't a single row or a single column of data. We have 2 rows of data in each age category. So this cannot be a goodness of fit. We are not comparing one row of data against some sort of population. So for example, if we were saying, according to the study in 2010, this percentage of people in each of these age groups use online social networks. Now we have this sample. Does the sample support, is the 2010 distribution of social network use among these age groups still correct, or has it changed? Okay, that would be in a situation where we'd use goodness of fit test. But we're having two different lines here, so that cannot be goodness of fit. Describe how these data could have been collected so that a test for homogeneity is appropriate. So we have a two-way table here. Is this a test of homogeneity or a test of independence? Well, without knowing how the data is collected, we can't say for sure, although I do have my opinion about which one it probably is. If the two groups were sampled independently, okay, so for example, if you went on some sort of social network site and you randomly selected people from that network site and you found out what age group they were in, and then you did the same thing, you found a whole group of people that don't use the social network at all. That would be hard to do, actually, to find that, I think. And then randomly selected from that group and wrote down their age and put them in categories. That would be a way to do a test of homogeneity. And you would say, is the distribution of ages the same for those who use social networks and those who don't? That's how you would ask the question. But it would probably be really difficult to collect the data that way. Most likely this is a test of independence. In a test of independence, you would just get a random sample of people and you would ask them two questions. How old are you, and do you use online social networks? And then you would record their answers in the correct category. That's probably how the data would be collected. So one sample with two questions versus two samples with one question. Okay? Homogeneity, two separate samples, ask them one question, their age. One sample, ask them two questions, their age and their social network use. That's the difference between independence and homogeneity. In general, that's what I just said, okay? Homogeneity, two or more groups and one question. Independence, one group and two questions. So let's look at an example down here. In here, I want to look at one that could be done either way. In a study reported by Annals of Emergency Medicine in March 2009, researchers conducted a randomized double-blind clinical trial to compare the effects of ibuprofen and acetaminophen plus codeine as a pain reliever for children recovering from arm fractures. There were many response variables recorded, including the presence of any adverse effects such as nausea, dizziness, and drowsiness. Here are the results. Okay, so we have two treatment groups. Children were randomly assigned to get one or the other of these pain-relieving medicines. Then, after the study was conducted, they were measured. Did they have adverse effects, nausea, dizziness, or drowsiness, or did they not? And then they were put in those two possible categories. So if you have two separate groups with only two possible values for the variable, you could do a test of homogeneity, but you could also do a two-proportion z-test. So if it is a 2 by 2 table of data, then you could use a two-proportion z-test. You could define p either as the percentage of adverse effects or the percentage of no adverse effects. So I said, let p be the proportion of people who would have adverse effects from the drug. Notice I said who would have, because that would be like in general in the population, not people who did have in the sample, because I don't need to infer anything about the sample. I already know what the sample says. So in other words, I would have one sample proportion would be 36 over 122 for the ibuprofen group. The other would be 57 over 112. If I go in and do a two-proportion z-test, you'd have to put in x1 and n1 and x2 and n2, do a not equal to. You get a p-value of 0.00084. If you do a chi-square two-way test, you get the same p-value. So you can do either test and you'll get the same results as far as significance. The only difference is if I wanted to know which one's greater than or less than rather than just not equal to, the two-proportion z-test would allow me to do that instead of just looking at is there an association. It would give me more information about the type of association and the direction of the association.